Welcome back to our Chem 152 video series. In previous examples, we've used Ka and Kb to find pH. In this example, we'll do the opposite, and we'll use pH to find a Kb value of a weak base. This question says we have a 0.1 molarity solution of NH3, and we're given a pH value of 11.127. The goal of the question is to find the Kb value. To start off, we're going to write a reaction of that NH3 with water. The fact that we've also said that this will have a Kb value tells you that NH3 will be a weak base. Let's say NH3 plus water yields, with a double arrow, some conjugate acid and some conjugate base. Let's remind ourselves that NH3 is a weak base, meaning water must act as an acid. A weak base will gain H and go more positive. If we have NH3, we're going to go up to NH4 and go more positive. The acid, water, will lose an H, giving us OH, and since acids go more negative, we'll have OH negative. We are also given that our solution of NH3 is 0.1 molarity, and this information goes on the initial line on our table. Since we have no information given for NH4 positive or OH negative, they'll both have 0 for their molarity. In previous examples, we've put X for our change. However, this method is slightly different because our pH value will give us the information about the equilibrium line. But first, what we have to do to use that information is convert the pH value to a concentration. We have two options for what equation to use to reach that concentration. We can say that pH is equal to negative log of H3O, or we could say that pH is equal to 14 plus the log of OH. Since OH is a member of our equation and H3O is not, it makes more sense to use the second option. We already know the pH is 11.127, and we'll place that in the pH position. This will equal 14 plus log of OH. Now subtract 14 from both sides. We will end up with negative 2.873 on the left and log of OH on the right. Now, to get OH rather than just log OH, the step that we use algebraically is not particularly obvious. For those of you who have taken a math class recently, you might remember that to clear a log from an equation, we must use a base 10 exponential. So we'll start by writing 10 on the left and 10 on the right. On the left, we'll have 10 raised to the negative 2.873. And on the right, we'll have log of OH. However, since base 10 exponential and log are inverse functions, they both cancel. Therefore, we can say that our OH is going to be 10 raised to the negative 2.873, which we can find in a calculator. We'll get 1.34 times 10 to the negative third molarity. This number is what we will place for our OH concentration, and we will place it on the equilibrium line in this position. With this one piece of information, we can complete the rest of the table and eventually find Kb. Now that we have 1.34 times 10 to the negative third in the equilibrium position underneath OH, we can deduce that the change from 0 to 1.34 times 10 to the negative third is just plus 1.34 times 10 to the negative third. This also means our change for NH4, since it has a coefficient of 1, just like OH, will be exactly the same number. We can say the same thing about NH3, except for we must lose some amount of NH3 because it's a reactant. We'll say negative 1.34 times 10 to the negative third. Then we can either add or subtract to get the equilibrium concentration. 0 plus 1.34 times 10 to the negative third gives 1.34 times 10 to the negative third. We can subtract 0.1 minus 1.34 times 10 to the negative third in a calculator. We will get 0.0987 molarity for NH3. Now to find the Kb, we can take the products over the reactants. Our products are both 1.34 times 10 to the negative third, so we'll place that in a parentheses and we'll say squared because there are two of them. On the bottom, we'll say 0.0987 since that is our reactant. Again, water will not impact our K value at all because it's a pure liquid. Now, we'll take the division. We'll end up with an answer of 1.82 times 10 to the negative fifth power, and that will be our Kb of our weak base. The reference value for this is actually 1.8 times 10 to the negative fifth if you check the literature, and so the answer we found is very close to that. And so based on the pH, we can find the Ka or Kb of a weak acid or a weak base. Just remember that the pH goes on the equilibrium line, not the initial line. Thank you again for watching, and we'll see you again soon.